Hi, this is Phil from Simply Rhino. In this video I'm going to be taking a look at KeyShot version 9. This new version of KeyShot contains a number of enhancements and new features. But here I just want to take a look at the 5 new tools that I think will be of most interest to Rhino users. KeyShot 9 introduces a new geometry node type called Fuzz. This is ideal for creating short pile fabrics such as the covering on this tennis ball. As we zoom into the image, you can see clearly how KeyShot creates the individual fabric pile strands. Extra realism is added by the ability to vary the length and the direction of the strands, and of course there's full control over the strand thickness, density and color. Before we look at setting up the tennis ball material, let's take a quick look at the basics of the Fuzz geometry node. Here I have a single surface imported from Rhino to which I've applied a simple KeyShot material. To add the geometry node, I click on Material Graph to open up the Material Graph editor. If I right click on the canvas, I can navigate to Geometry and then select Fuzz to add the Fuzz node. Next I need to connect the Fuzz node to the material, and then to see the adjustable properties of the Fuzz node I just double click here. I'm now going to rearrange the desktop to make it easier to show the effect of adjusting these properties. Once the geometry node has been created, in both the Fuzz properties dialog and the top right hand corner of the preview window there will be a button to execute the geometry node. This allows me to see the effect of the properties set out here. Both the length and the radius of the strands are set either explicitly or via a slider. The default proposition is that the strands are grown in the surface normal direction. If I want to reverse this direction, then I can simply use a minus value in length. If I want to add variation to the length of these strands, I can use a value in the length variation here or pull the slider to the right. So I'll set a value to 1, execute the geometry, and you can see I now have a variation in the length of those strands. I can also adjust the density of the strands, again either by slider or by a specific value. So I'll just reduce this density a little bit and reduce the radius and execute. Maybe reduce the density a little more. And then I want to look at adding some randomness to these strands. So I'll put a value of 2 into here and execute the geometry node, and this randomizes the direction of the strands. Because this randomizes the direction, you may see that some of the strands will now build underneath the surface. Having established the randomness, I can then increase the segmentation of the individual strands. The value shown here is 4, and you can see that each strand effectively has 4 segments. If I increase that to something like 40, for example, you'll see that the strands appear to be smoother in their deformation, and the shape is now more convoluted. So I've now increased the density of the strands again, and finally I just want to look at appearance. This allows me to change the material properties of the strands, and if I just quickly change the color here, you'll see that I can do this without having to execute the geometry node. If, however, I just want to use the same material that is on the surface and apply that to the fuzz, then I can do this through the material graph. So I just need to take, in this case, the advanced material and plug this into the fuzz surface. In this instance, when I do this on the material graph, I'll need to execute the geometry node here to see those changes being applied. So you can see that the fuzz material, with some adjustment and experimentation, can be used to simulate a range of materials, including organic matter like grass and vegetation. Let's now take a quick look at the tennis ball render, and I'll start by looking at the Rhino geometry. So this started off as a primitive sphere and a 2D curve. The 2D curve was projected onto the sphere in the top view to give us this three-dimensional curve. Next, I created an ellipse that was aligned normal to the sphere and was centered about the projected curve. Next, I used sweep one rail to use the projected curve as a rail and the ellipse as a cross section. This produces a solid elliptical profile sweep. The sweep was then removed by using a Boolean difference from the sphere, resulting in this shape. And finally, a small fillet was added at each side of the recess. At this stage, the geometry is a closed polysurface or solid, and so I split out the individual surfaces to separate the tennis ball seam from the fabric surfaces. The tennis ball geometry is then imported into KeyShot 9, and to create a product design style render, I'll first of all go to environments, and I'll use a little bit more of a contrasty environment. I'll go to lighting and switch to product mode lighting. I'll then go into environment and just choose a white flat color for the background, turn on my ground shadows, and also use the occluded ground shadows. Then if I go to materials, you'll see that I created a couple of basic materials already here. The seam material is a plastic material, and this has a bump texture on it, and this is mapped with triplanar mapping. This is to represent the rubber material that is used on the tennis ball seam. The fabric material at the moment is just a fairly straightforward advanced material, and as previously shown, I'm going to open up the material graph and I'm going to add the fuzz geometry node. So once again, we right click on the canvas, geometry, fuzz, plug the fuzz into the fabric material, double click to open up the fuzz options. I'm going to keep the material at default at the moment so that it's easier to see the strands, and I'm going to zoom in to the tennis ball. I'm going to set the length and the diameter of the strands to start off with. So I'll start with a length of 0.8 of a millimeter, and the radius I'll set to being 0.01 of a millimeter. I can leave the other settings at default and execute the geometry node. Okay, and we'll see the strands appearing from the tennis ball. Now, I am just going to create a few more of these by increasing the density, but I don't necessarily want to make this too dense at the moment because I want to see what the individual strands look like. So I'll just increase the density slightly, and this will give me a better idea of the sort of size of the material. I can close up the density later on. So I'm going to introduce a variation into the length, and most important, I'm going to introduce some randomness. So when setting these values, it's a good idea to set these one at a time so that you see the changes as they're made. Maybe reduce the length now slightly, 0.6. Okay, then I'm going to introduce the randomness. So I'm going to use a value of about 2.5 for this. And again, I'm going to execute that node. Okay, now at this stage, these are very basic segmentation. So I really want to increase the segmentation here. So I'll turn this up to something like 20. And they look now much more like fabric strands. Okay, so this is probably the sort of thing that I'm looking for. And now I can increase the density. So I'll increase this to a value of around 16. Okay, so as this starts to refine on screen, we can now see that this looks pretty nice. We're seeing the individual strands here. They're not too long. Maybe we should just increase the density slightly more. So let's maybe up the density slightly and execute the geometry node again. Okay, so that's starting to look better now. And one of the reasons why I don't want to have the strands the same color as the underlying material to start off with is because I can see the density and I can see the individual strands much more easily. So once I'm happy with this, then I can just apply the material color to this. So let's just sort out this window here. So then I take the advanced material and plug that in to the fuzz surface. Okay, and remember that I'm going to need to execute that geometry to see that material change. Okay, so you can now see we're starting to get a really nice realistic covering now on our tennis ball. Denoise is a new feature in KeyShot 9 that produces clean images much more quickly. This works in both the real-time and rendered views and with CPU or GPU acceleration. This is a model set that we use in our KeyShot training classes, and as I'm sure you're aware, the real-time preview is essentially constantly ray tracing and refining. So as I zoom in, you'll see the image re-renders. And of course there's a certain amount of time before the image settles down and the noise is removed. I'm going to add a stopwatch and move the image and then just start the stopwatch and have a look at how long it takes for the noise to clean out. So we're around 20 seconds now and there's still quite a lot of noise around here, and also you can see noise here, predominantly in the shadow areas. Gradually now this noise is getting softer, being gradually cleaned out. Let's stop it here around 40 seconds. Okay, so you can see that image looks okay, and of course this will keep refining. Let's now have a look when we turn on the denoiser. So we can turn on this either here in the ribbon at the top or under image and denoise, and we've got a control for how much denoising we actually employ, a slider control. Okay, so I'm going to move the image, start the stopwatch, and you'll see how the noise gets broken down into larger areas as the noise is gradually smoothed out. We're into 10 seconds now. Most of the noise around here is gone. It's a little bit blurry around here. Most of the noise has gone over here. So if we stop this around here near 20 seconds, you can see this is looking pretty good. So we have a really big improvement in speed of cleaning up the image when we use the denoiser. So once again you can see how it looks at the noise intelligently, and then removes that noise. However, it does this without losing any of the sharpness. You can see the edge of the hex head screw here is very sharp. This edge around here is very sharp. And of course the text is very sharp around here. So it's a very clever way of denoising the image. So this is of course all in the real-time image, but we can also use the denoiser in the rendered image. So I'm going to reset the view a little bit here. One thing that is useful for Rhino users is if you go to Edit and Preferences, you can change the direction of the mouse wheel so that the zoom behaves in the same way as it does in Rhino. Okay, so I'm going to just look at this area here and I'm going to render out an image. So first of all, I'm going to turn off the denoiser, and my render is set up to a particular ratio, and in options here I'm just going to let this render out for 1 minute 30 seconds. So this isn't going to be by any means a high quality render, but if I do this with and without the denoiser, you'll see the difference in the two renders. So I'm going to let this render and then jump to the end of this rendering. Okay, once this render reaches the end, you can see that there's still quite a bit of noise in here in the shadows, a little bit of noise inside of here, the hex head. It's quite noticeable along here and also up here. Okay, so this is typical noise that we get in any renderers inside the sort of shadow areas. We get this speckly noise. Okay, so let's close that image down and we'll turn on the denoiser and render again. And once again, I'll jump to the end of the render, or nearly the end of the render. So as we get towards the end of the render, you can see at this stage this looks exactly the same. And then you'll see that the denoising pass, there it goes on last of all, and this cleans up the residual noise. So now we have an image that is substantially cleaner than without the denoiser, and of course we've got no additional time incurred in that render. Now of course at the moment we're seeing these images at a reduced size, so I'm going to now jump into Photoshop and compare a couple of similar images in full size. So now here's the similar image at full size in Photoshop. I've split this into two layers, so if I turn off the top layer that has the denoising on, you'll see the image underneath here is the one without the denoiser, and you can see all of the graininess and the noise in the shadow areas all along here and underneath here. Turn the denoise layer back on again and you see that noise is cleaned out. So this is just a very simple example of a 1 minute 30 second render, and you can see how the denoise pass improves the quality of the image. KeyShot 9 introduces GPU rendering. GPU rendering or acceleration has been a much requested feature, and now we have the choice of using either CPU or GPU for KeyShot, real-time previews and renders. Now of course there are some requirements and caveats for GPU rendering, so let's look at these in detail. Firstly, this is an NVIDIA only solution. So if you have an AMD card, then at the time of making this video there is no GPU solution. Secondly, as this is an NVIDIA only solution, then effectively this becomes a Windows only solution, as all of the recent Macs with dedicated GPUs use AMD hardware. Next, Only NVIDIA GPUs based on Maxwell or later microarchitecture are supported. So in Quadro terms, for example, if you have an M4000, P4000 or RTX 4000 card, then your hardware is supported. Next, and probably most important, GPU acceleration is optimized for NVIDIA cards with RTX ray tracing cores. This is where we expect to see the most significant performance gains with GPU rendering. We'll be testing KeyShot with an RTX based solution in a separate video. But for now, we're going to look at GPU acceleration on a machine with the previous generation Pascal based card. Before we do this, the last important step is the NVIDIA driver requirement. KeyShot requires driver version 435 or upwards. To find out what graphics driver you have, you can double-click on your Windows desktop and open the NVIDIA control panel. If you then click on System Information, you'll see both the driver version and the type. If you have a more recent Windows 10 installation, then you may require a DCH driver rather than a standard driver. Both versions are available. So if we jump to the NVIDIA website and I look for a driver for my laptop which has a Quadro P3000 card, you'll see that there's a choice of standard and DCH driver type, and also a choice of optimal ODE driver or a new feature QNF driver. At the time of making this video, you'll need the QNF driver, as the older ODE driver is currently not at a high enough version. If you have a GeForce rather than a Quadro card, then again you'll have a choice between the Studio driver and the Game Ready driver. In the case of KeyShot, again at the time of making this video, you would need the Game Ready driver. Now let's take a look at GPU rendering in action, firstly in the real-time view. For this CPU-GPU comparison, I'm using a PNY Prevail Pro laptop with a Core i7 7700 HQ processor. This has 8 logical processors running at 2.8 GHz. The graphics card is a Quadro P3000 with 6 GB of RAM and 1280 CUDA cores. To see the effects of the GPU acceleration, I'm going to use a small utility called GPU-Z. This will allow me to show the loading of the graphics card. GPU is turned on here in the ribbon. With GPU and the denoiser turned on, if I now switch views, we can see how quickly the denoiser clears out the noise from the image. The denoiser works slightly differently, it seems, with GPU acceleration turned on, in that the noise in the shadows is cleaned out very quickly and it takes slightly longer to resolve some of the highlight areas. However, if we again switch view and now turn off the GPU acceleration and go back to the large view, you'll see that clearing out the noise here is noticeably slower when we are relying on CPU. When I enable GPU, you'll see that immediately the graphics card is nearly being used at 100%, and as I not only navigate around the view but let the view refine via ray tracing, the GPU is being loaded almost at maximum. So KeyShot seems to be making efficient use of the GPU. Now remember, however, that KeyShot is optimized for NVIDIA RTX cards, and what we're seeing here is the previous generation Pascal card. GPU rendering is going to also affect our final renders. So I'm going to switch to this view, and I'm going to pause, and I'm going to turn off GPU acceleration initially, and I'm going to create a render. So I'm going to render this out at HD resolution, 1920 by 1080 pixels, and I'm going to set a maximum number of samples for the render to produce, and I'm going to choose 120 samples, and I'll start the render. So the render's now underway, and we're zoomed in fully to the render, and I'll skip to nearer the end of this render process. So the render's completed, and just wait for the denoising pass. And we can see that that render has taken 7 minutes 39 seconds. Okay, so let's now switch to GPU. Again, we'll use the same settings that we had previously and hit render. You can see that again GPU now is being used at maximum, so all of the processing of this image is being passed on to the graphics card, and again we'll pick up the render towards the end of those 120 samples. Okay, so again we're coming towards the end of the render, and now the denoiser pass is finished, and this has completed in 97 seconds. So that 97 seconds is just over 5 times faster than rendering with CPU. So let's take a look at these images at full size and see if there are any noticeable differences between them. So I'm now inside Photoshop comparing the two images. So we're looking at the CPU render at the moment. If we switch to the GPU render, you'll see there are some small differences. This rubberized material here is rendered slightly differently. If I just toggle between the two, you can see the differences. And the GPU render is possibly very, very slightly lighter on this edge here. If we zoom in to 100% on both images, firstly with the CPU render, and now with the GPU render, there is possibly slightly more noise in the shadow here, but this is a very small amount. But to counter that, you could say that the way that the rubberized material has been rendered with GPU looks slightly more realistic. But in truth, there's little difference between the two images. They are subjectively different, but they are both good quality images. So although there are small differences, I think it's fair to say that we can see there's a clear performance gain to be had in using GPU rendering. Here's another example of the CPU versus GPU render. Given the different technical challenge in rendering the fuzz material, this time the GPU advantage is less and approximately twice as fast as CPU. This is the CPU image, and if we switch to the GPU image, you'll see the only real difference is in the shadow area, which is slightly darker. If we look at the shadow area at full size, you'll see that both images have smoothed out the noise. This is the CPU render, and this is the GPU render. The tennis ball material looks almost exactly the same, and the shadow is smooth on both, but slightly darker on the GPU version. KeyShot 9 introduces a new material type called real cloth. This is an excellent way of creating woven materials with full control over the warp and weft and other fabric parameters, even including details such as tension, fiber density, color variation and flyaway fibers. Let's take a look at how we apply and control this material. Here I'm starting with a surface I've imported from Rhino, and this just has the default black material that you'll see if the object properties in Rhino are left at default. If I double click on the material icon, I can get to the settings for the material, and I can change the material type to real cloth. Firstly, we can set up the scale of the woven pattern in either scene units, which in this case are millimeters, or in UV parameters. So I'm going to choose scene units, and to explain the scaling a little further, I'm going to open up the weave pattern editor. The surface that I have here in Rhino is approximately 100 by 100 millimeters. So if I set the scale to 10, and this value is the thickness of the fiber, and then if I make the width of the fiber a full thickness value of 1 and apply, you'll see that we have a 10 by 10 thread matrix. So each one of these squares is, in this case, going to be 10 millimeters, and the value we put in for the width here is the width of the thread relative to the 10 millimeter square. And this is the preview of the pattern. Now, of course, this is oversized just to actually show the method by which the scaling works. So I'm going to reduce this size, and another really important thing that it's very easy to do with real cloth is to make the fabric transparent. So these black areas that we see between the threads will now appear to be transparent. So this is a really easy way of creating technical fabrics. For example, we have a lot of customers in the shoe industry, and the ability to overlap technical mesh fabrics over the top of each other is going to be really useful. So you can see here that we have a number of standard pattern sizes. Each time we change the pattern, we are going to need to apply that pattern, and we can choose the width of the fabric and select whether that fabric is a round or a ribbon type of fabric. We can also adjust the tension. If I close down the weave pattern editor, let's have a look at the other properties that we can adjust. So as we've mentioned previously, scale is done either on a slider or on a numerical basis. We can change the angle by which the pattern is applied, so the rotational angle of the pattern, and we can add an element of distortion into the pattern to make this look more naturalistic. And then we can add anti-aliasing to soften the hard edges. This might be particularly useful if you're using transparency, just to soften the edges of the fabric around those transparent areas. We can then adjust the color of the warp and the weft individually. It's not just the color that we can adjust the roughness and the refractive index, so we can really start to make these materials more of a synthetic material, even a more metallic thread, by increasing the index of refraction and reducing the roughness. We can add a color variation into the fabric, so that in this case the warp color is varying. This adds some naturalistic values to it. And then we can also increase or decrease the fiber density and increase the detail of the fibers. Particularly useful if we go into close-up into the fabric. So we've got an awful lot of control here over the fabric. So we're now much less reliant on using bitmaps as a starting point, because we're actually creating this fabric entirely from scratch. If I just zoom in to a small area of the fabric, and the other thing that we can add here, which gives added realism, is the flyaway fibers. And this is using something similar to the fuzz that we've looked at previously. And when we check this box, all of these parameters here will become live: the density, radius, length, and I'll either need to use this button here, execute geometry node, or this button here to create those flyaway fibers that you can see here. So I'll just increase the density of those and the radius slightly just to make it easy to see them, and increase the saturation, and then re-execute those. Okay, so you can start to see now a few flyaway fibers on the edge of the fabric. And so you can see that in KeyShot 9 we can easily create realistic woven fabrics with full control over the pattern and fabric parameters. KeyShot 9 now has a 3D model library. There's a new model tab in the library, and that contains access to a few primitives and backdrops. But more important, we can access the cloud library. As well as having materials, environments, backplates and textures, there's now a full model library containing fully detailed and textured models. To access these models, we just simply choose the model that we need. So, for example, I'll navigate to the coffee maker and I just download that, and I'll scroll down a little and pick one of these nice looking pastries and download that. And once these models are here, they can simply be dragged and dropped into our scene. We can then just position these, and here we'll see the model already textured and ready to go. With some of the models, for example the wood floor pack, which I've now loaded into the scene, these contain multi-materials so that I can choose from a variety of different material finishes for my flooring, all of which are just packaged with the model that I've just downloaded. So that's about it for this video. Please feel free to leave any comments below, and if you found this video useful, please hit the like button. To keep up with all the latest Rhino and KeyShot news, please subscribe to this channel. I'm off for a coffee now, so thanks very much for watching, and I hope to catch up with you again soon in the next video.